Some of you asked, okay, first of all, let's begin. Welcome back. Some of you asked me to repeat gradient descent. I know I kind of started something in the end of the lecture and couldn't finish it, so we are going to repeat it a little bit more today, like in the beginning of the lecture. There were few anonymous feedbacks from the Google form, like so. Well, I'm kind of going to mix the feedback from both the courses because these are general feedback. Okay, so I don't know which course it was, but somebody complained that I move things too fast. Like for example, like when I swipe, the content disappears, so you're not able to take notes. I'll try to be a little bit slow, but one general tip, but at least for this class, this is at 12:30, right? Like the oral class is at 9:30 in the morning. It's difficult to print, but for you, I highly recommend you to print the notes before the lecture, so that you don't need to write everything by yourself. Of course, it's a good habit to write and take notes. Like it's going to add things to your memory, but at least you know that you have the content. Like you don't need to rush to copy everything, because I know that I write too fast. Okay, so like I don't expect you to write that fast. At the same time, I assume this is better than showing you equations in slides, because then I just swipe slides and there are like 7 equations to copy, right? Like so, there's a trade-off. I'll try to be a little bit slow, but please interrupt me like in between if I'm writing too fast or I'm swiping too fast. Okay, so you don't need to wait to go back and give this feedback in anonymous form. Like you tell that right now, and I will adapt my speed. And other than that, I guess I actually uploaded notes for even for the next week. Probably now that I'm 1 week ahead, like in 2 days, I'll upload the notes for the like week later. Okay, so now you have more time with the notes for you to either read them or print them or do whatever. Okay, and assignment 1 was out last week, right? So after today's lecture, like you would have everything that you need for finishing assignment 1, and it's a relatively simple assignment in the sense experiments doesn't take too much time. It's linear regression. If you are not using Colab, I highly encourage you to go check Colab. You can do your entire assignment in Colab and then download the notebook and then write your reports based on that. Okay. Any questions about assignment?
Yes.
Yeah.
I think in the model selection part, we have a question about training and validation and then test. When we don't, you mentioned that we should use any regularization, so we don't have any hyperparameter. Why we should work on the validation?
Oh, okay. So if you're not doing any model selection, just report whatever the performance with validation set is. It's still a proxy, right?
Okay.
Okay. Well, there was also another feedback. Again, I don't remember from which course, that I don't check the chat often. I'm sorry. So this is supposed to be an in-person class. Like I'm trying to accommodate people who cannot be here remote, like to join remotely. The problem is there are a lot of conversations that is going on in the chat, so I cannot read the entire conversation. So I don't know how to differentiate questions from conversations. Like probably when I say, is there any questions, like copy paste your question again so that I don't miss it. Okay, so you can also use raise hand. Then I'm going to ask you to directly ask your question. Okay, so let us start. Just as a quick recap of what we have seen in the previous lecture, like so, we spent a lot of time on linear regression, right? Regression in general, right? Like so, like we started with linear models for regression. Right? So something like y of y hat is equal to summation over, let's say j is equal to 0 to p. There are p features, wi xi, right? Something like this. Like so, like a simple linear model, which is linear with respect to the parameters as well as the input, right? Like so, and we also discussed that this kind of linear models are restrictive in the sense they can only model straight lines. Like if you want to model anything other than lines, like some nonlinear stuff, like then this is not a good model, right? Like so, we looked at one potential way to resolve this problem, which was through the lens of basis functions, right? So basis functions, like what are basis functions? Like so now, if you remember, this is your system. It takes x as input, and it has some parameter w, and it makes some prediction y, right? Now, there are two ways to add nonlinearity to the system. Like the system itself could behave nonlinearly, right? So which means your system is nonlinear with respect to the parameter w, which is a complex system. We will see it, but not in the next few weeks, like a little bit later. And the cheap option to create nonlinearity is actually through the input, right? So if you take the input x and convert it into something like phi of x, where phi is some fixed nonlinear function, then you are introducing some nonlinearity here, which means you can now model any sort of lines that you want, right? Like it's a nonlinear, right? Of course, it depends on what functions you are using. Like we looked at Gaussian basis functions, like polynomial functions, sigmoidal functions, and so on, right? Like so, this is one way to make the system nonlinear. And for now, like at least for the next like 1 or 2 weeks, like we will just stick with this form of nonlinearity. Okay. The reason why this form of nonlinearity is interesting is because even though there is some nonlinearity, the system is still a linear model, right? Like because the system is still linear with respect to the parameters w, which means you can find closed form solutions. Okay, so then towards the end of the previous lecture, we started discussing what if I cannot find closed form solution? Like, so what if I have a nonlinear model, like, or a model which is not, where it is not easy for me to come up with a closed form solution for finding the parameters, right? Like, so then we discussed the idea of gradient descent. Right. So to quickly recap, like what we saw in the previous week, but we are going to repeat it again, is the idea of gradient descent is to come up with an iterative solution for finding the optimal parameters. And the way in which we are going to do that is by starting with some random parameters to begin with, and then you compute the gradient like of the loss function with respect to these parameters. The gradient is going to tell you like the maximum, and then you just it gives you a positive slope. You take a negative step, which so that you can go down and minimize the loss function, right? Like so, for example, if this is my loss function, then we know that this is the minimum that I want to achieve, right? Now I randomly pick a point. Okay, this is my current parameter configuration. I compute the gradient. It's going to give me this slope. Okay. Now you take the negative of that. So that is going to tell you this slope, right? So maybe a different color. This slope. Now you don't want to take big steps. Like you want to be careful about your steps. So we add a hyperparameter like step size or learning rate, so that you take only fraction of steps. Is that right? Okay. Now that was gradient descent. So now maybe let's repeat or reformalize gradient descent. Okay, so we are in the linear regression setting, okay, where y hat of x comma w, we're just going to consider simple like one-dimensional input. Okay, so now so that we can visualize these things. So it's going to be w0 plus w1x, and the parameters in this case are w0 and w1, and the loss function in this case, let's just call it as, so this is a function of w0, w1, right? So if for every possible w0, w1, you have a model, and this model is giving you some loss. So it's a function of w0 and w1. So this is going to be 1 over 2n summation over I is equal to 1 to capital N y hat of xi, give it w, minus y of I the whole square. right? And our goal here is to minimize the loss. Find W0 and W1 such that this loss is minimized, right? So now, as we discussed before, this is actually a simple problem. We can actually find analytical solution. But for now, we are going to assume that we don't know how to do analytical solution here. So how can we solve this problem using gradient descent, right? Like so, well, I think I forgot to copy paste the figure. So let's go to the previous lecture notes. I think I forgot the spotlight. Okay. Yeah. Yeah. So here you can see the visualization of the loss surface for various values of W0 and W1. Okay. So I'm going to randomly pick a W0, W1. Okay. Let's say I pick like W1 is equal to 10. Let's say I pick W1 is equal to 10 and W0 to be minus 20. Is that what this point is? Minus 20, 10. Yeah. Okay, so you pick random values for W0 and W1, and then like now you evaluate your loss, and this is the loss, corresponding loss. Okay. Similarly, you can try every possible W0, W1, and then you plot this mesh or grid, which has like the complete loss surface. Okay. Now the first thing that we can notice here is like this seems to be a very nice loss function because there's only one minima here, right? So for this whole loss surface, like there's only one minima, which is here, right? So now the good thing is like if you do gradient descent here, like by starting from a random point, like you slowly walk towards the minimum, you will always reach the optimal solution because there's only one minimum, right? I think last week somebody asked what if there are more than one minimum. We're going to talk about it today, but for now, at least for this linear classification, like linear regression problem, like so we have a very nice, well-behaved loss function where there's only one minimum, and gradient descent would find it, right? Now, what was the algorithm? Now, the basic idea here is we are going to repeat until convergence. Okay, so each parameter Wj is going to be Wj minus alpha times dou by dou Wj of the loss function. Like you're going to do this simultaneously for both W0, so J is equal to 0 and J is equal to 1. Okay, now in this case, this alpha is the step size or learning rate. It's a hyperparameter that you have to tune, and this is the gradient. Okay, now we also discussed if alpha is too small, then you're going to take a lot of time to converge because you're taking very tiny steps. Okay, on the other hand, if alpha is too large, then you can easily overshoot the minimum, and you can even like you can fail to converge and even diverge. So as I mentioned in the previous lecture, so this is probably the most sensitive hyperparameter or the most important hyperparameter that you will see in the entire course. Okay, so there are various other hyperparameters that you are seeing, but this is one of the most crucial hyperparameters that you should always tune. Okay, now this is fine. Now, in the case of linear regression, we know our loss function. So what was our loss function? Our loss function was W0, W1 is equal to 1 over 2n, summation over I is equal to 1 to capital N, y hat of xi minus y of I, the whole square, right? Now, I just need to compute the gradient of this with respect to W0 and W1. So now, dou L by dou W0. So what would be that? So you have 1 over 2n, summation over I is equal to 1 to capital N. Okay, So this is x squared. So when you differentiate, you get 2x, right? So you put 2 in the front, and then this you have this whole thing. So y hat of xi w minus y of I. Okay. Now I differentiate this term inside. So probably I will expand this term so that it's easy for us. So it's w0 plus w1 x of I minus. Okay. So now I differentiate this term with respect to w0. What would that be? 1. Okay. Now similarly, dou L by dou W1 is equal to 1 over 2n, summation over I is equal to 1 to capital N, 2x. So W0 plus W1 xi minus y of I. Now what happens if I differentiate this internal term? Sorry?
xi.
It's xi, right? So, okay. So now we have the gradient descent algorithm. Like, so you can just repeat until convergence, like these two gradient updates simultaneously. Okay. Any questions about?
Excuse me.
Yeah.
Would you please go back to the slide that you have like 3D surface? My question is why you plot like W0, WL, and then actually loss functions all together.
Okay. Okay. Well, I think I moved things too fast. Okay, now it's working. Well, in this case, like what I'm really trying to do is like I'm trying to visualize how the loss surface is looking like. Okay, so now your loss is computed from the model, right? Like, and your model is defined from W0 and W1. So for every possible W0 and W1, you're going to construct a model, and this model is going to have some loss function. So the goal is to find that one particular model which has the minimum loss, or in other words, to find that one particular W0, W1 that has the minimum loss. So in this case, all I have done is like I tried every possible combination of W0, W1, and I computed the loss. I'm visualizing this loss. So my 2 dimensions here are W0 and W1, and the third dimension is the loss. Is that clear? Okay, any other questions? Okay, well, I have to move really slow for the camera to capture things. Okay, so now I have a small animation of things that I found online. So in this case, it is the same loss function, right? So you can see that the gradient descent starts here. So after many, many steps, it reaches the star. So the interesting thing here is like it always reaches the star. Like every time you try, like in this case, it's starting only from the same place. But for this loss function, you can start wherever you want. You will always reach the star. Okay. So where star is your local optimum. Okay. So why is it the case for linear regression? Okay. So let's talk a little bit about the special nature of linear regression loss function. So in the case of linear regression, if you have one-dimensional input, then your loss function would look something like this, okay? Where you have a single minima. Okay? If you have a two-dimensional input, your loss function will look like a bowl, and in n dimensions, it's a hyperbole, right? Now, this loss function, the least square loss function, is an example of what is known as convex function. Okay, so I think this week's reading will be about convex functions. I haven't added it to the schedule. I'm going to add it after the lecture. But well, this is not an optimization course, so we will not study convex functions in general. But we are going to talk a little bit about them because the role of convexity and non-convexity in machine learning is huge. Okay, so now the beauty of convex functions is that they always have a unique global minimum. Okay. Now, the least square objective that we saw in the linear models is just one example of convex function, but you could construct many other convex functions that you want. Like probably we will see one or two of them in the lecture, in the course. Okay. Now, this convexity is easy to obtain if you have linear models. Okay. However, if you have non-linear models, which is what we are most interested in, right? Like, so we want more powerful models, like, and more nonlinear models. Like, now in those cases, you might actually get non-convex loss functions. Okay, so what do I mean by a non-convex loss function? Like, it is going to have many minimums. Okay, and like for example, like one example could be something like this. Okay, it looks like a very irregular loss function. In this case, like, what is the global minimum? Yeah.
We are not sure we're converging to the lowest minimum.
Yeah, yeah. Oh, yeah, yeah. But what is the local minimum here? The second one, right? So this one. So this is my global minimum. However, there are many other local minimums possible in this loss function. Like, for example, this is a local minimum, this is a local minimum, and this is a local minimum. Right? Now, if I do gradient descent with this kind of loss surface, okay, and let us say we start somewhere here. Okay. Now, gradient descent will start moving towards the minimum, and the moment it sees the first minimum, it's going to get stuck there. Okay, there's no way it is going to escape this and move to the next. Okay. Now, this is a problem because now the initialization matters. You randomly initialize here, you reach here. You initialize here, you reach here. If you're lucky and you initialize here, you will reach here. Okay, yeah.
With a different step size, could you maybe jump over that local minimum and reach another?
Okay, so that's a good question. So can we just increase the step size so that we can reach, like we can overshoot?
If you tune it right.
Right. It is possible, but as you can imagine, it's really hard, right? Like, so, like, because you don't have any knowledge about how the loss function looks like. So these pictures that I show here, or even the bowl that I showed here, like, the reason why I took 1D, 2D examples is so that we can visualize the loss functions. But in real applications, like, you might have millions of variables or parameters, right? Like, and like in that case, like, you cannot visualize these loss functions. So you have no idea about like how the loss function looks like, which means overshooting. Like, you're taking a risk by increasing the step size, right? Like, so it's not impossible, but like it's just very hard. Okay. Now, so this shows that initialization itself is a hyperparameter, right? Like, so in nonlinear models, you should try different random initializations with the hope that one of them is going to get to the minima that we want. Okay. So now you understand the intricacies, right? Like, so you have a model, you don't change anything, you just change the initialization, like how you are initializing your W0, W1, W2. Okay. Now, depending on how you initialize, your gradient descent is going to take you to different minimas if it is not a convex function. Okay. So now, is there anything that we can do?
What about using derivative of it? Like,
Sorry?
can we use first like the function, we get a derivative of it, and then do that?
Sorry, can you repeat, please?
Yeah, use, for example, the function is nonlinear and it's, for example, a cubic function. You use the derivative and do the steps on it.
Oh, yeah, we are doing the derivatives. Like, so when I say we are doing gradient descent with this nonlinear model, then we are taking the derivatives and taking steps by alpha times the derivative. Okay. But even then, there is no guarantee that you will reach the local minimum, like global minimum, because of, well, because there are multiple minimums and because gradient descent is not a powerful algorithm to skip minimums. It's like, again, go back to the blindfolded analogy, right? Like, so you're blindfolded and like you are in this terrain. Okay. So you reach here. Now, how would you know that this is not the global minimum, right? Like, so there is no way for you to, like, you try taking a step in all the directions, they are all going up. So now the only possible explanation for that is like you are in a minimum and you don't know if there is any other better minimum, so you just stay there, right? So, question? Do you have any question? Yeah. Okay. Okay. So now we're going to talk about like another variation of gradient descent. Okay, so which is stochastic gradient descent, which might avoid some of the problems of gradient descent. Okay. Now, if you remember, our loss function is a sum of n different terms, right? If there are n examples in your data set, so your loss function is given by summation over n loss with respect to the nth example, right? Now, to make every gradient update, you have to sequentially go through all the examples and compute the gradient with loss with respect to these examples, take gradients with respect to these examples, and then you sum them, and then you take a step, right? Now, imagine you have millions of data points. Now, to take even one step, you have to iterate over a million examples, compute the loss, compute gradients, sum them, and then you take one step. Okay. Now, you can do better than this if you start approximating this loss function. Okay. Now, instead of considering all the n terms in the loss function, like what if I approximate with just one example? Okay. Now, then my gradient descent update rule becomes w is equal to w minus alpha times dou by dou w of just the loss with respect to kth example. So this is for a random data point. Okay. Okay. Now, first of all, this is an approximation, right? So why is it an approximation? Because instead of considering the complete loss, I'm assuming that this one example is representative of the data set. So I'm approximating, and hence like this is stochastic gradient descent. Okay. Now, this helps us in updating much more frequently than waiting for all the million data points to be seen. Okay. But there is also an added advantage here. So the added advantage is, since this is an approximation, this approximation is going to introduce noise, right? When I compute gradient with respect to just one example, okay, it is not going to be in the same direction as if I would have computed with the entire data set. Okay, let us see some cartoon explanation. Like, for example, let me try a different color. Okay, let us say I am here. Okay, if I take the true gradient descent, like with the complete data set, there is no stochasticity involved, which means it will point me to only one direction, which is this, right? On the other hand, let me change the color. So let's say we have a green color, which is for SGD. Okay. So now let's say I do SGD from here. Okay. So there's a noise involved, right? Like, so maybe this SGD will point me towards a different point. Okay. So for example, let's say, so since these are one example, like the variance might be high. So if you are lucky, it's going to point you here, which means you will reach here. You would have never reached here with gradient descent. Okay. So now on an average, you might converge here, or maybe, okay, maybe the next gradient could put you here. Okay, we don't know. But the point is, this noise can also be useful. Like, this noise can help you to like escape local minima and reach global minima. Okay, is that clear? Any question about stochastic gradient descent? Yeah.
In every step, we choose the point randomly, yes? So in each step, we choose randomly.
Okay, so that's a good point. So we are going to talk about the details now. So maybe before I talk about the details, let me write the algorithm. So, well, the algorithm is simple, like it's same as the gradient descent, except that we are going to use only one example here. Okay, so it's basically repeat until convergence. Okay, now we are going to go through all the examples one by one. Okay, so for I is equal to 1 to n. Okay, now W0 is equal to W0 minus alpha times y of xi minus y of I, and W1 is equal to W1 minus alpha times y of xi minus y of I multiplied by x of I. Okay, now I said you randomly pick an example, right? But we just want to make sure that we are picking all the examples, like we don't miss examples. Okay, so one way to achieve this is by going through your entire data set one at a time. Okay, that is why we have this for I is equal to 1 to n. Okay, now this whole loop of going through the data set one by one from beginning to end is known as epoch. Okay, so some people call it iteration, like you can have different names, like but for us, like to be consistent in the course and in assignments, they are going to call this as epoch. So when your assignment asks you to do 100 epochs, it means you go through the data set 100 times one after another. Okay, now as one can imagine, if you don't randomize and just go through them one at a time, then you might have some examples which cancel out each other in their gradients. Okay, now which means your result is conditioned on the order of the data set. Now we want to remove this conditioning. So what you would normally do is in the beginning of every episode, you would shuffle the entire data set. Okay, if you have 100 examples, the beginning of every episode or in the beginning of every epoch, you shuffle them, go through that order. In the second epoch, you reshuffle, go through that order, and so on. Okay, so that anything that was canceling the previous epoch will not happen in this epoch. Okay, now this kind of stochastic gradient descent, as we have already seen, has many benefits. Like the first benefit was it's faster to update, right? You don't need to wait for the entire data set to complete. Second benefit was it can skip local minimum, right? Now, there is also another benefit which is very realistic in terms of application as well. Like, so there are a lot of applications where you have to learn online. Okay, so consider a situation where the data is coming in as a stream, a continuous stream. Okay, so it's so much data that you cannot store it. You have to process it and throw it right after that. Okay, in this case, you cannot do full batch gradient descent because the data is a continuous stream. You cannot wait for the entire stream to come before learning. And there are many situations where you have to learn, like act immediately without waiting for the entire data set. Okay, so especially if you have a deployed system. Okay, now there is one query from the first user. You cannot wait for 100 more queries to come before you act. So you have to immediately act and like learn from what you have done so that the second query make it better, right? So in these kind of like online learning situations, okay, so you can only use SGD, not full gradient descent. Okay, now in one end we have, let's just call it full batch gradient descent. Okay, the complete true gradient descent. And in the other hand, we have stochastic gradient descent. So this is n examples at a time. This is one example at a time, right? So this is a true gradient. On the other hand, this is like a highly variant gradient, but where variance is useful, right? Like, so now you can kind of get the best of, well, there's also another issue. Okay, so when you use full batch gradient descent, you can exploit a lot of matrix computations and GPUs and hence train faster. Okay. However, if you're doing stochastic gradient descent with one example at a time, then you're only doing matrix multiplied by one vector. Like it's not a matrix multiplication, which means you will be slower. Okay. Now, one can combine the benefit of both by doing what is known as mini batch gradient descent. Okay. So the idea of mini batch gradient descent is to pick k examples instead of one examples. Okay, k random examples where k is much lesser than n. Like imagine you have 1,000 examples in the data set. You can set your mini batch size to be 10, which means you divide these 1,000 examples. Well, first you shuffle these 1,000 examples. Then you divide these 1,000 examples into batches of 10. You go through these batches like one after another. Okay, so that is mini batch gradient descent. So in practice, well, I think your assignment is asking you to do SGD and full batch GD. But in practice, like we will be using mini batch gradient descent more often. Okay, so like you will use it anyway in the future assignments and in your Kaggle competition. So okay, so any questions so far? Yeah.
Is there a defined way to find K, like how many examples you should for mini batch G?
That's a good point. So, well, simple answer is there is no rule which tells you how to pick K. So K itself is a hyperparameter. Okay. So there are a lot of theory on like how K is affecting the variance and things like that. Like probably we will not discuss that too much here. But K is a hyperparameter. And often you will see papers using K sizes in power of 2, 64, 128, 1024. So this choice of power of 2 is just to make efficient use of GPUs. Like so, matrix multiplications with powers of 2 is like more efficient or slightly more efficient. So that's why you will see people using batch size of 64. 64 is not a magical number. So like you can use batch size of 10, it's okay. But it is just that probably instead of 10, like something which is 2 power K is going to be a little bit faster. Okay. Okay, so now there is one more important question, like before we conclude our discussion on gradient descent, which is basically when to stop any of these variants of gradient descent, right? So I just say repeat until convergence in all my algorithms, like so. But in practice, you will not converge, like so. Like how would you stop? Any idea? Yeah.
Could you compute the difference between each step?
Okay, so you compute the difference in updates between each step, and then you find a threshold to stop. Any other solutions? So any solutions from Zoom, like people remote? You can raise hand if you have solution. I'll just wait for 5 seconds before I give chance to people in the room. Okay, well, I hope you guys are still hearing me. Okay, they are hearing, but they don't want to answer. Okay. Okay, the same threshold solution in the Zoom, but maybe someone here, like so, somebody.
If we value the difference in parameters between two different above are less than a fixed value, then we will stop.
Okay, so that's the same answer, like thresholding. So I'm looking for alternate answers here. Yeah.
When you meet KPT conditions, first order optimization condition.
Okay, so when you meet the first order optimization conditions. Okay, any other answers? Well, maybe we should have had some quiz component in the course. Okay, so somebody says define maximum number of steps. Is that an optimal thing to do? Like what if you don't converge before the steps, or what if you have converged already way before the steps, right? Okay, I told you that K is a hyperparameter. So how would you pick K? Yeah? Sorry, not K. Oh, okay, sorry. I didn't, okay, so K is batch size, sorry. Now, yeah.
Well, for most hyperparameters, we pick them with the validation set.
Yes.
So you could just treat the number of steps as.
Yeah. Okay. So that was the answer I was looking for. Okay. So now you can consider this number of epochs to be a hyperparameter itself. Okay. So how many number of epochs to run? Like how many steps of gradient descent to run? Okay, so whenever I say, okay, let's just call epoch, irrespective of which algorithm you are using. If you're using full batch gradient descent, then one step is one epoch. If you're using stochastic gradient descent, then n steps. Okay, so you have steps, which is gradient descent steps, and then you have epochs, right? Like so, for full batch gradient descent, like one step is one epoch, because in one step you see the entire data set. Now for SGD, n steps is one epoch. Can someone tell me what would be the number of steps for mini batch SGD?
N by K.
Sorry?
N by K.
N by K, right? Like you have n and your batch size is K. So n by K steps is one epoch. Now, how many epochs to run? You can treat this itself as a hyperparameter. The moment you treat this as a hyperparameter, then the best way to select that is by using the validation set, right? So normally, when you do gradient descent, you're going to plot number of epochs in your x-axis and your loss in the y-axis. Okay, so you will monitor two types of losses: training loss and validation loss. Now the training loss, as you can imagine, is going to be always going down, right? So the more you train, the more you fit to the data. So provided you have enough capacity, this loss is going to go to 0 at some point, right? So this is the training loss. But we know that 0 training loss doesn't mean anything about generalization, right? Like, so for generalization, we care about validation loss. So you can take the validation set and compute your loss with respect to the validation set. And that loss will be decreasing. And at some point, it is going to increase. Okay? Now, as you can guess, this is the region of overfitting. Okay? Which means you should stop here. And the corresponding number of epochs is here. Okay? But I have a question here. So how would I know that this is where I should stop, like when I am training? Okay? So what if my validation loss looks something like this? So what if my validation loss goes up? What if my validation loss looks something like this? I always draw nice pictures, right? Like, but in practice, it will not be the case. So when you implement things, so like, how would I know that this is the minimum or this is the best validation loss? Any ideas?
You can stop after seeing that number of epoch has been spent, but the loss was still increasing. So at the end of the curve, you can realize that after, for example, 1,000 epoch, the loss was still increasing. So you can estimate that it will keep increasing and not find another low minimum.
Okay, so in some sense, okay, so a practical way of doing this is by deciding, well, you don't need to go 1,000 epochs, 2,000 epochs, okay? So sometimes these epochs are costly. So maybe for your assignments, it's like 1 minute, but for most of the real application, 1 epoch might be 2 days. Okay, so you definitely don't want to do 1,000 epochs. So what people normally do is to define this notion of patience term. Okay, so you define some patience term. Let's just, okay, I have already used the K here, so I'm going to use P. Okay, so you decide some patience term. Let's say P is equal to 5 epochs. Now, whenever for consecutive 5 epochs your loss is increasing, then you will assume that, okay, we are overfitting, so I'm going to stop. Okay. Also, whenever you find your loss to be minimum, you checkpoint that model so that you know what is the best model to use. Is that clear? Any questions? So you will be implementing this idea. So, okay, so this idea has a name. So this is called early stopping. So whenever you do gradient descent, you will always do early stopping, like so that you don't need to run it for indefinite number of time. Okay, so it's called early stopping because you're stopping even before it converges. Okay, so any questions? Yeah.
What if our loss is still going down, but ever so slightly until a point where it's like it's converging and whatnot? Is there like a way to mitigate this?
Yeah, so that's a good question. So like, what if your validation loss is not going up, but just flattened, right? So it could happen. So then even in that case, you could use the same patience. Like, so for example, like the way to define patience is like, if my validation loss is not improving for the next K epochs or P epochs, this includes staying at the same time, say same level, right? Like, so you could cover that case here. Any other questions before we stop? Yeah.
So for the gradient design, you mentioned we should update the parameters simultaneously. Can you explain it more? When we have the parameters in the loss function, so we should update all of them and then update the loss function?
Okay, so well, you compute the loss, then you compute gradient with respect to each of the parameters, and then you update those parameters, all the parameters, and then you go to the next epoch. Like, so when I say simultaneously, it doesn't mean in the same time. It just means that you finish that process before you go to the next step. But in practice, when you implement these things, you will be implementing them with matrix notation. So you will be updating all the W's in parallel. Okay, any other questions? Okay, so we will stop here and take a 10 minutes break or 11 minutes break and start at 1:45.